Hello, we are the carbon capture team. Today we will present our project proposal on development of a carbon dioxide absorbent using PAN-based nanofibers. Here is the presentation outline: introduction, research goals, experimental methods, research schedule, and team introduction. First, let's talk about the background of our research. Since industrialization, the Earth's average temperature has increased by 1.2 degrees Celsius. This is very close to the 2.0 degrees Celsius limit set by the Paris Agreement, with only a 0.7 degrees Celsius gap remaining. If we were to stop this temperature rise, extreme heat, heavy rainfall, ecosystem destruction, and food shortages will become serious problems. Not only humans, but all living organisms will suffer. This is why we want to contribute to reducing global warming. Many global efforts are being made to reduce carbon dioxide emissions. The Paris Agreement suggests solutions such as renewable energy, carbon-free power, CCUS, and DAC. Since most of these technologies export DAC are already commercialized, so we decided to focus on DAC technology.
I will explain the principle of electrospin. On one side, there is a cylinder containing the liquid to be fabricated, and on the other side, there is a collector to gather the fibers. When a high voltage is applied between them, the liquid at the tip of cylinder becomes charged with the positive polarity. That cause molecules of the liquid to push each other and to form a pointed shape, which is called a Taylor cone. When the reflux force continues, the liquid is drawn out from the tip of the Taylor cone in the form of the thin thread. The traditional method relies on physical absorption using van der Waals forces. However, we will use urea to enhance both physical and chemical absorption, increasing efficiency and selectivity.
To test the performance of our nanofibers, we will use a custom-made chamber. This chamber will include HC05 module to transmit data wirelessly, MHC19 sensor for measuring CO2 concentration, and 2 fans for air circulation. We will use a carbon dioxide injector to set the carbon dioxide concentration inside the chamber to 4,800 ppm. Then, we will use an air circulators to ensure that the incoming air passes through our filter. Here is a diagram of our chamber. To ensure accurate results, we will prevent outside air from entering.
Now we will introduce how to test the sample. We will conduct 3 experiments. First, inject carbon dioxide without nanofibers and measure concentration changes. Second, repeat the experiment with PAN nanofibers. Third, use urea-added nanofibers and compare all results. Our goal is to absorb 2.4 per milligram of carbon dioxide in a 33,304.24 cubic centimeter chamber in the third experiment. Next, we will introduce expected results and conclusion. We predict that when carbonized fibers made of PAN, DMF, and urea are in the chamber, the carbon dioxide concentration will decrease the fastest, and the case that fibers made of PAN and DMF are in the chamber will be the next. We expect that when there is nothing inside the chamber, the carbon dioxide concentration will decrease way or slower than other two cases. We anticipate that carbonized fibers composed of PAN, DMF, and urea will be able to capture 2.0 or per milligram of carbon dioxide within a 33,304.24 cubic centimeter chamber. DAC is a powerful carbon dioxide reducing technique. It is expected to be a promising future technology, and nanofiber shaped adsorbent will be a key role. Now we will introduce our project schedule. April to May, nanofiber production. April to June, carbonization process. Afterward, we will conduct regular experiments. Now we will introduce our team rules. 태준, nanofiber production. 수영, SEM analysis. 혜빈, sensor connection and chamber setup. 정우, carbonization and experiments. With effective teamwork, we aim for a successful study. Thank you for your attention.